Welcome to this first of hopefully many live streams where I'll be going through just mostly questions on the different topics that I'm talking about. It would be really helpful if, I know we only have two people watching this currently, but if you could give some form of interaction so I know I'm not just talking to myself the entire time, that would be appreciated. So if you do have any questions, then this is a great opportunity to have some sort of tailor-made tutoring on this topic for you. So please do put any questions that you have in the chat so that I can sort of tailor this session to the people that are actually watching it. So my basic plan for this session is going to be thinking about the different energy stores, what they are, how to recognize them, and then crucially, what that actually translates to in questions. So we'll be spending a bit of time going through lots of different exam questions which relate to energy stores and sort of working out how the theory will translate into an actual exam question. So exactly what you need to know and how to use it. Once we've looked at sort of the general energy stores and what they are, we'll then be moving on to calculations using them. So calculations form a large part of any physics exam. Even the centre assessments that you're going to be doing if you're in year 11 will have a large proportion of calculations in them. Some of that is remembering the equation, but a large part of it is remembering how to use an equation and being really careful that you're not making silly mistakes while you're doing it is really important. So with regards to calculations, we'll initially be having a look at calculations involving kinetic energy, gravitational potential energy, and elastic potential energy. So these three, actually I'm going to be combining them in one slightly weird, not normal question. And we'll have a look at a process for tackling calculation questions. Once we've done this, then I'm hoping that either someone will have a question and we'll be able to go through that, or if there are no questions, then I think that'll probably take us around about half an hour. And if no one's got any questions, then we'll stop it there and just do a half an hour blast for this first one. And then we'll see if there's an appetite to do any more of these later on in the coming weeks. If you do have any further questions that I'm not answering, then feel free to go on to one of the videos on the channel. There's one where I do an energy question, a fully worked question, and post on there that you'd like to have some more help on a particular topic, and then either I'll start a live stream for that or I'll record a video for it. So I'm not going to start this proper until past, because that's when this was going to be published, but that is basically what we're going to go through. The way I'm going to talk about it is for the current GCSE, particularly for AQA, and they're the questions that we're going to be looking at. However, the energy topic is pretty consistent across all exam boards at the moment, or generally physics. So if you are watching and your exam board is not AQA, then that doesn't really matter. Right, okay. So one more repeat, if anyone would like me to go over something other than these things, or in addition to them, if you can say something, that would be brilliant. Okay, for the two people still watching, let's go. So, the energy stores are all about sort of saying that energy is this universal quantity. It's a way for us to be able to quantify whether something is or is not possible. What energy itself is actually beyond our understanding, definitely beyond GCSE, but actually beyond physics' understanding in general. So we don't need to understand what energy is, we just need to be able to calculate it and recognise the different store that it might be in. For example, two of the energy stores are gravitational potential energy, which I'll call GPE for the rest of time, because otherwise It is a bit long-handed to write out. And kinetic energy. So the energy concept is just a number. It's a way of calculating what's going to happen. So gravitational potential energy is all about things being raised above a gravitationally attractive object, say the planet. So GCSE, you can just say it's being raised above a planet. The reason it's a potential energy is because it's being placed within a field where something has the potential to happen. Because let's say I had an object up here. Okay, so if I've just raised a tennis ball up, say, if I let that go, it's going to fall down. So you might say, okay, so it's not potential, it's going to happen. But if I say put it on a shelf, it's still gained potential energy. I have still moved it above the planet, but it doesn't have to fall down. It might do. It has the potential to if I remove the shelf, but it doesn't have to. So if I did remove that shelf, then it'll start moving. And so it's losing gravitational potential energy, but one of the big rules of energy is that it cannot be created or destroyed. So it's going to transfer that energy from gravitational potential, which is about things being moved up above the planet, to kinetic energy, which is about things moving. So here we have an example of how we have different stores, and these stores of energy are just sort of stating how that energy is being held at that one moment in time, but it can also be transferred between these stores. And because it's a quantity, that means we can calculate how much energy is transferred from one to another, and as you'll see in the questions that I do later, that starts to actually say we can make calculations to work out what future values are going to be. For example, if I knew how high up it had been lifted, I'd be able to work out how fast that ball could be moving when it reached the floor. Okay, so I've mentioned GPE and KE. We also have thermal, gravitational. We have elastic potential energy, which I'm going to call EPE. We have chemical. We have magnetic. We have electrostatic. We have nuclear. And am I missing anything? 1, 2, 3, 4, 5, 6, 7, 8. No, that's all of them. Okay. So the ones that you need to be able to calculate are gravitational potential energy, kinetic energy, and elastic potential energy. You will not be asked to calculate anything with the other energy stores. You will, however, have to be able to recognize them. So you'll recognize gravitational potential energy because something will either have been raised up or something will be falling. There will be a change in height. So if there is a change in height, delta meaning change in, then you can be pretty sure that gravitational potential energy is involved. A classic sort of way of saying that it's not gravitational potential energy, which you'll come to in some questions. I have one of these in the first energy question that I covered on my channel, is to say that it is on a flat road or a flat surface. So the height is not changing. You'll recognise that there is a change in kinetic energy if there is a change in speed. So if there's a change in speed, that means there's been a change in kinetic energy. Because kinetic energy is all about the energy stored within moving objects. Thermal energy, well, that's a change in temperature. So if you increase the thermal energy store of something, you're increasing its temperature. Incidentally, increasing the thermal energy of something actually is sneakily just changing the kinetic energy of the particles within an object. So watch out, oh, can't quite see that. So watch out for that, that if you're actually just changing the speed of the particles, think about this particularly when you're looking at gas pressure laws, that kind of thing, you're increasing the temperature of an object, but the kinetic energy of the individual particles. So EPE, elastic potential energy, this is if something is being stretched or squashed. Chemical energy is one of the ones where actually there's the most variation in what it can be. but quite often, if there is a person involved doing something, then you're going to say that the energy store to start with is a chemical energy store. So you eat something that provides your body with energy that it can then do things with. But this is also quite often comes up when you're talking about batteries or anything where there's sort of chemical bonds or chemical reactions taking place. So that one's quite broad. Magnetic, well, if there's a magnet involved. And then electrostatic, this is if charges are involved. So sort of charged particles, so we're thinking static electricity, that kind of thing. Nuclear, well, this one I've put over to one side because this is really to do with the idea of fission and fusion. There is energy stored within the very structure of atoms itself, but this one gets more looked into in a different type of topic. Right, so what we're going to do now is have a quick think about some exam questions and sort of see where we can identify the need to look at these different stores. Okay. So here we have an exam question which is about energy. So you can be looking at this. So images showing a student before and after a bungee jump. Bungee cord has an unstretched length, and we're seeing there is a bridge and there's after. So hopefully when you see this, you think, okay, it's an energy question. What sort of energy stores are going to be involved? Well, we have a change in height, so that should hopefully be suggesting to you that gravitational potential energy is involved, and we have an extended or a stretched cord, so hopefully you'll be thinking elastic potential energy. Okay, so here we have the classic question for can you identify the energy stores, a gap fill. Okay, so before the student jumps from the bridge, he has a store of some energy, and when he is falling, the store of something energy increases. So you're generally looking for a before and after story. It's the idea of what do they start with, and then what is that being transferred to. So before the student jumps from the bridge, he has a store of something. So we need to be thinking what's going to change once he jumps. So once he jumps, he is starting off high and then ending up low. So hopefully that should say to you, before the student jumps from the bridge, he has a store of gravitational potential energy. When he is falling, the student's store of something energy increases. Okay, so we need to think what is changing as someone is falling. Well, with bungee cords, they're not going to be storing energy until they are stretched. So there is a certain length anyway, so it has an unstretched length of 20 meters. So when they're falling, what is changing? Well, when something falls, it accelerates. That means that its velocity or its speed is going to be increasing. So if speed is increasing, well then that should tell you that kinetic energy is changing, and because you're increasing in speed, you're going to be increasing the kinetic store. When the bungee cord is stretched, the cord stores energy as something. Well, we've got that keyword stretched in there, so hopefully that should indicate to you elastic potential. So this is an example of the type of question that commonly sort of draws on the what are the energy stores and what are the transfers taking place. And it's all about recognizing these different things. It's all about trying to recognize what is changing. Because if you can identify what is changing in each individual case, you should be able to work out which store is involved. Okay. Right, let's move on from looking at these stores to looking at calculating them. So as I said before, you need to be able to calculate gravitational potential energy, kinetic energy, and elastic potential energy. So if you're going to calculate something, then you're going to need to know the equation for it and what the different symbols mean. So for gravitational potential energy, the GPE, which is going to be measured in joules, because all the energies are the same, so they're all measured in joules, that is equal to mgh. And remember, when we write the letters next to each other, there's a hidden multiplication sign in there. So the m, that is the mass of an object. G is the gravitational field strength, or the acceleration due to gravity. So gravitational field strength. And h, that is the height. You might see this written as delta EP, so the change in energy potential, gravitational potential energy, is equal to mg delta h. Now, the reason for this is generally we are looking for changes in gravitational potential energy, because to calculate the absolute gravitational potential energy means you need to be able to state where you're starting your height from. Things that land on the floor still have a gravitational potential energy, because if you removed that floor, they would continue falling. So to get around this, we tend to say we're going to look at the change in gravitational potential energy, and so the change in height becomes more relevant. Okay, so that is for gravitational potential energy. Kinetic energy, or Ke, again measured in joules, is equal to 1/2 times the mass times the velocity squared, or the speed squared. The reason we can say velocity or speed interchangeably is velocity would be a vector quantity, so it could have a plus or a minus. But if we had a minus in there, because we're squaring it, minus times a minus is a positive, so this will always be positive. So 1/2 is just 1/2, and again we have the mass times the speed squared. The final one you need to calculate is the elastic potential energy, EPE, again measured in joules, and that is equal to 1/2 times K times E squared. Okay, so 1/2 is 1/2 times K, which is the spring constant. So this comes in from the forces and motion topic, so Hooke's law. You can find the spring constant there. That's a paper 2 topic. And E stands for the extension. Crucially, when you're calculating these, all of these will have to be in base SI units. So for mass, that will be kilograms. For speed, that will be meters per second. The spring constant is newtons per meter, and the extension is in meters. So there you go. These are the 3 equations you need to be able to use. So let's have a go at using them. Okay, so a car of mass 2,000 kilograms is travelling at 20 meters per second. Calculate the kinetic energy of the car. So I would suggest that whenever you're doing calculation questions, you look at them using a method that you use the same way every single time. And I call this method EVS, which is my acronym that stands for equation, variables, substitution, and solve. Now, quite often people will say, but this is an easy question, I don't need to go through this process. But it's one of those things of training yourself to make sure you're consistent with what you're doing. Because if you're being consistent with what you're doing, then you'll do it more frequently, you'll do it more accurately, and you'll go through it every single time, so that one time when it might matter, you've still got it. Okay, so I propose this system because it does 2 things. One, if you don't like rearranging equations and maths isn't particularly your strong point, it vastly simplifies the maths. And secondly, it forces you to set out your work in a way that will help you gain the most calculation marks if you get the final answer wrong. Because you'll have shown each step of the way, so it makes it really easy for an examiner to work out where you might have gone wrong yourself. Okay, so equation. That is identifying which equation the question is asking you to use. Because generally you'll be asked to use maybe 1 or 2 equations maximum. but for most questions it'll be one equation. So for this one, we're being asked to calculate the kinetic energy of the car. The kinetic energy. So we know we need to do the EV system because we've seen our key command word calculate. We know it's about kinetic energy, so we need to write down the equation for kinetic energy. Ideally, you should write it out in full in words so that an examiner can easily see what you're writing, and it's harder to make a mistake like writing the wrong letter because that's what you thought the symbol was. For space today, I'm going to write them in symbols. So KE is equal to a half mv squared. Great. So we've got that. The second part, variables, is really carefully stating what the different variables are and then taking them out of the question and into your answer. Because this way you've shown to the examiner that you have been able to work out where the key information is in the question, and also if this is the point that you make a mistake, then it's obvious to yourself and to them what has gone wrong. So if I say k equals a half mv squared, so I can say that I need to have ke, don't know what that is. A half isn't a variable, that's a number. I've got the mass. The mass is 2,000 kilograms. Kilograms, that's an SI unit, don't need to change it. And then the speed, that's equal to 20 meters per second. Okay, so I've got my variables, I've got my equation. Now what I need to do is I need to substitute the values in. So that means I'm not trying to rearrange, I'm just trying to put numbers from here into the equation. So ke is equal to half times 2,000 times by 20 squared. Okay, now we've got to our final section, the solve section. So this is where we put our numbers into the calculator and we see what comes out. Half times 2,000 times 20 squared. And it comes out that that is 400,000 joules. At this point we can stop and we can think, okay, can we do a sort of an idiot check on this? Does that number seem about right? Well, you can relate this to sort of the energy of lifting something up. Now, a car with a mass of 2,000 kilograms traveling at 20 meters per second, that sort of sounds like it should have a lot of energy to it. Okay, so 400,000 joules, that's sounding about right, so I think we're good there. Okay, we're now going to do a three-part question. So a three-part question which is going to link all of these three energy stores that you need to be able to calculate together. So, part one. A car rolls down a hill that is 10 meters high. The car has a mass of 2,000 kilograms. How much GPE has it lost? Okay, so it's rolling down a hill, so it's going to be losing gravitational potential energy. So I'm going to give you a moment just to have a think through. Can you identify which equation you're going to need to use? How would you go about this? Okay, so we're going to be using EVs again. So equation, that's the first step. So this is asking how much GPE has it lost. Okay, so I need to have the equation for that. So what is the change in energy potential? That is equal to the mass times G times delta H. So G at GCSE in physics is equal to 10 newtons per kilogram. Okay, so we know that that is what G is, and so I can write that in my variables section here. What is the change? Well, we don't know, that's what we're looking for. The mass is equal to 2,000 kilograms, and delta H, well, it's rolled down a hill that's 10 meters high, so that's going to be 10 meters. Technically, you might be able to put negative 10 because that is what it's losing energy, but because we're saying how much has it lost, we can keep this positive. Okay, so we've got our variables, so now we need to substitute it in. Delta EP is equal to 2,000 times by 10 times by 10. Now, this is a nice simple one because we're just multiplying by 2 sets of 10. So I'm not going to worry about the calculator, but it's a physics exam, so you can always use your calculator. So that's going to be 200,000 joules. Okay, and remember to add your units. So we have our part 1 done. Fantastic. So a car rolls down a hill that's 10 meters high. The car has a mass of 2,000 kilograms. How much gravitational potential energy has it lost? That's how much it's lost. Right. So that was part 1. So thinking, yeah, great. I've got a simple equation. I can apply it. But now we get on to the sort of level 8, level 9 type of question. How fast is the car traveling now? Now we're going to be assuming that it's not transferred energy into any other stores. This is a perfect world where energy just goes into the stores that we want and nothing's wasted. So in this case, we can imagine that all the energy is going to be transferring from gravitational potential energy to kinetic energy. So the first thing to recognize is that energy is not created or destroyed, so we can assume that all the energy that was lost from the gravitational potential energy store will be transferred to the kinetic energy store. Okay, so how fast the car is travelling. We're making that assumption. So the first part of EVs is to write the equation. So how fast is it travelling? Well, how can we relate speed and energy? Well, we can think of kinetic energy. So Ke is equal to a half mv squared. So we've got our speed in there, so we can find out how fast it is. Right, where are we going to get this from? So now we go through variables. Ke. The kinetic energy is going to be equal to the energy that's been lost from the gravitational potential energy. That's where the energy is coming from. It's being transferred from one store to the other store. So we can take our value from the previous question, which is 200,000 joules. Okay, a half is a half. The mass is equal to, well, again, we can take it from the previous question. It's equal to 2,000 kilograms. And the velocity, I'm just going to call it the velocity squared now. We don't know. Okay. So a lot of students, when they get to this point, they go, oh, I need to rearrange the equation, and then get into a real muddle because there's squared terms. It's going on. So I will show you how to rearrange it in a second, but first we'll just look at it, what it looks like when we just put numbers in. The substitution section. So we can say that 200,000 is equal to a half times 2,000 times v squared. Now I could slip another s into EVs, and I'd call that simplify, because now I've got one unknown. So actually I could make this much simpler. I could say, okay, what's a half times 2,000? That's 1,000. What's 200,000 divided by 1,000? Because if I simplify this, I can say that 200,000 is equal to 1,000 v squared. So quite simple. So if I'm going to start to find v, what do I need to do? I need to get it on its own. So 200,000 is equal to 1,000 v squared. So I could divide through. So 200 is equal to v squared. So that would suggest that the square root of 200 is equal to v. Okay, so that means that v is equal to, well, 10 root 2, but we could round that to being 14.4 meters per second. And actually, this is the first time that we've actually identified the point in doing energy calculations. We've taken a piece of information that a car is rolling down a hill. We know how high that hill is. And from that, we're able to make a decent prediction at how fast that car is going to be travelling at the bottom of that hill, just by doing some energy calculations. Right, so that's in the simplified version. If you think your maths is stronger, then actually you could rearrange this. We could say that we want to get v on its own, so we need to get rid of the half first. So 2 KE, 2 times KE divided by the mass, all square rooted, is equal to V, which is what we've done here. But this I did all in one step. This one I put the numbers in first, I simplified it down so we've got fewer terms, and then we worked through, and you'd find we'd get to the same answer. So how fast is the car travelling now? 14.1 meters per second. Okay. Now, this last part of the question requires a bit of a stretch of the imagination. So in my sort of fake world in which this is acting, I'm now stopping this car from travelling by hooking a spring onto the back of it and letting it extend. So I'm transferring that energy from kinetic energy into elastic potential. So it's a bit ridiculous, but equally, that's what I'm going with. Although I say this is ridiculous, but there is an extent to which... camera's gone out of focus. The extent to which this is used as a system, things do have tether lines, do get hooked onto basically bigger rubber bands to slow them down, so it's not too ridiculous. Okay, so the car is stopped by hooking a spring to it, the spring extending. The spring constant is 40 newtons per meter. Okay, so again, I'm going to use EVs. What's the equation here? Well, we need to be thinking about a spring which is extending, so hopefully that should suggest to you we're talking about elastic potential energy, which is equal to a half times K times E squared, where K is the spring constant. So now we need to write out the variables. EPE, well, that's going to be all the energy that went to KE, which is going to be all the energy that came from GPE, so that will be 200,000 joules. What's the spring constant? Well, they've told us the spring constant is 40 newtons per meter. What's E squared? Well, we don't know. Okay. So actually, this is looking pretty similar to the previous question, just with a different value in there. Okay. So we now need to calculate this. Well, no, now we need to substitute in the values. So 200,000 is equal to a half times 40 times E squared. So we can add in that extra S, the simplify. Let's just move that over so you can see. So we can say that 200,000 is equal to 20 E squared. Okay, so we can then divide that through and square root it. So what is the square root of that? We can just pop that into the calculator. So hopefully you've got there before me. E is equal to 100 meters. You can see why I said that this was a bit of a ridiculous question. Okay, we have now reached that half an hour mark. So this is the point at which either someone asks a question about anything within the energy or the electricity topics. I'm happy to cover other things that we've not looked at so far, or we will call the stream there. And if you do have other questions, then you can find one of my other videos on the channel and post a question there. So I'll give a minute or two just to see if anyone does have any questions. If you do, just pop them into the chat and we can go through them. But if not, I will end the stream there and we'll take it from there. Okay, looks like that is probably all we're going to do for today then. If you have found this helpful, then consider watching the playback, seeing if that was helpful. And if you do find it really helpful and want to have another one, then please sort of leave a comment on the stream or like it. Sort of shows me that it's been a helpful exercise and something I should do again. If you didn't think it was helpful, then feel free to dislike it. And I won't do them again. But other than that, I will say thank you very much. Hope you found it useful, and goodbye.